Today I'll be doing LeetCode Weekly Contest 178, and I'll be explaining my solutions after I solve all the problems. This is just simple for loops. Oh wait. Oh, the answer is a vector. Oh, do we have to check which? Oh, okay then. Okay, and then Okay, we'll do a DFS also. DFS will check. Something's wrong with this. Oh, wait. Okay, this looks good. The first one is false for some reason. So there's nothing in head, none. Okay. True, false, okay. I think this is a pathfinding problem. Oh wait, I should... Wait, 1 is j plus 1. And 2 is j minus 1. And 3 is I plus 1. Okay. Okay, I think this is how you write 01 BFS. I'm not exactly sure. Oh, that was a typo. I'm very glad the sample test caught that typo. Okay, this should be good. Now, let's see. I feel like I was a bit slow. Accepted. Yeah. If I'm actually third, then it's not that bad. Okay, so for the first problem, basically you loop through I to find the answer for element I, and then in order to find the answer for element I, you have another loop inside this loop, and for each of the elements, like j, you check if j is smaller than I, and if that's true, then we add 1 to the answer because we're supposed to count how many numbers are smaller than it. And then we return the entire list of answers. For the second problem, so first you need to go through all of the votes, and then you should count for each team the number of first place votes it has, the number of second place votes it has, and so on. So in my code here, basically, first I assume that all 26 teams are included. Then I create a matrix of m by m plus 1. And each row of m plus 1 elements, the first m elements will store, the first element will store the number of times it appears as the first vote, and the second element stores the number of times it appears as a second vote, and so on. And then the last element m, will basically just stores the index of the team. So I go through all the votes, and then for each element in the vote, I add 1 to the corresponding team, the corresponding index of the team, and I also and j is the place of the vote. So I add it to this matrix. Then I also insert this team into the set, so later I can figure out which teams are present in the votes. So then I go through each team and I set the nth element, which will be the index of this team. And then I need this because later on I sort this matrix T by the rows, so I need this index to be able to know which array corresponds to which team. So then I sort the matrix T, And then the way I sort is, first I compare the first m elements lexicographically. So if at any point the number of ith place votes is different for the two teams, then A will be ranked first if it has the greater number of votes at the ith place. And if they all have the same number of votes for each place, then I just return the team with a smaller ID, which is element M. And then lastly, I construct my answer. So I go through each of the teams in matrix T, and then first I make sure that the team actually exists in the vote. And if it does exist, which I check with my set over here, then I add the team to my answer. And then finally, I return the answer. For this problem, basically, what I do is for each node, I will set it as the starting node of the linked list. And then I'll check if the linked list works at that node. So the way I do that is I have a DFS, and then this DFS checks if we can start the linked list at any subtree at root. So in order to find the answer, I just call DFS root head because it checks all the nodes at the subtree of root. So the way this DFS function works is, first I check the subtrees of the left child and the right child. And if any of them work, then I just return true. But if none of them work, then I check if we can start the linked list from the current root node. And this is the function DFS2. So DFS says that DFS checks if the linked list can start at the subtree of root, but DFS2 checks if we can start at only the root, not its subtree. So the way this DFS2 function works is, if we reach the end of the linked list, then we basically return true because there's nothing to match. And otherwise, we have something to match. And if the root is null, if there's no node, or if the value of the root is not the same as the value of the list, then we'll return 0. And otherwise, that means we can match. Otherwise, we can match the value of the root with the value of the head. So now we need to match the next element in the linked list. And there are two cases for this. So the first case is if we match the next element of the linked list with the left child. So we call this DFS2 function on the left child. And the second case is if we match the next element in the linked list with the right child. So I call DFS2 here. And then I return, if one of them is true, then I'll return true. Yeah. Okay, so for this problem, it might not be obvious why this reduces to a pathfinding problem at first. But then, if you think about it, the way we can model this as pathfinding because, as shortest path, because, so we'll create edges with weight 0, and the edges with weight 0 basically are the edges which correspond to the direction on the grid. So if I go from here to here, that's weight 0, and if I go from here to here, that's weight 0. And then I set the weight to 0 because if we use this edge, then we don't need to change the direction of the arrow. Okay, and then there are also edges with weight 1. So if I want to go from here to here, then it will cost 1 because I need to move, and I need to change the direction of this cell. So basically for each cell, we create 4 edges. And then 3 of the edges, this one, and this one, the ones which do not point in the direction of the cell, they will have cost 1. And then the edge which points in the direction of the cell will have cost 0. And then, so we have a pathfinding problem on a grid. We have a shortest path problem on a grid with edge weights 0 and 1. This is almost like a breadth-first search problem, but it's not exactly the same. I used something called 0-1 BFS here, but you could also just use Dijkstra. So basically at first I have a double-ended queue, and the reason I need a double-ended queue is because in addition to pushing to the back of the queue, I might also push to the front of the queue. And that's why I need the double-ended queue. So everything is pretty much similar to a standard breadth-first search. So you have the distance matrix, and I also have a visited matrix. So at the start, I just take the first cell from the start of the queue. Then if it's already processed, then I just skip the cell. And then I set the cell to process. And then for each of the 4 neighbors, which is I coded here, Ni and Nj is the neighboring cell. Then first I check if the neighboring cell is within the bounds. And if it's not within the bounds, then I just skip this cell. Then I calculate the distance in order to travel to that cell. So the distance starts with the distance to the cell, and then if k plus 1 is not equal to the direction in the grid, that means we also need to add 1 to the distance again. And then finally, I check if the distance is smaller than the distance we already know in the distance matrix. And if this new distance is smaller, then we'll update the distance for Ni and Nj. And then here comes the interesting part. So if the weight of the edge was 0, then that means the distance is the same, and then we should push it to the front of the queue because the distance will be the smallest, so we should process it first. However, if the direction of the edge is not the same and the weight is 1, then we need to push to the back of the queue because we want to process it later because it has a bigger distance. And finally, we turn the distance to n-1, n-1. And this is basically it for these 4 problems. So if this video was helpful, then feel free to like and subscribe. And if any of the explanations were unclear, feel free to ask questions in the comments so that I can help you.